Welcome students to today's lecture. We are still continuing with thermodynamics aspects. So today we want to discuss open system steady flow energy equations. So in an open system, not necessarily steady, energy is transferred into and out of the system not only by heat and work, but also by the fluid that crosses into the subsequently out of the system in the form of internal energy, gravitational potential energy, kinetic energy, and flow. Some of the matter flowing through the system may also be retained by the system, leading to accumulation. The statement of the first law for such a general open system is energy entering a system must be equal to the energy leaving the system plus any accumulation of energy within the system. This must be clearly understood, students. Energy entering a system must equal the energy leaving the system plus any accumulation of energy within the system. So in engineering, we often encounter problems concerning steady flow processes, like the rate at which the fluid flows through the machine or apparatus is constant and there is no accumulation within the system. The following conditions must be satisfied. So the first condition is that the mass rate of flow into and out of the system are equal and do not vary with time. The energy of the fluid both at the entrance and exit does not change with time. The rates of heat and or work transfer across the system boundary do not vary with time. So as scribbled here in the figure 1.4, in an open system, you can see the mass flow rate dm.1 in bracket pressure 1 times volume 1 plus internal energy 1 plus the kinetic energy C1 squared over 2 plus the potential energy GZ1. This is what is getting into the system, and then we have the work that is done by the system and heat added to the system, represented by delta W and delta Q respectively. Then at the output, what leaves the system is the mass flow rate 2, pressure 2 times volume 2 plus internal energy 2 state 2 plus speed, the kinetic energy state 2 plus potential energy state 2. So therefore, if we organize this in an equation using the first law of thermodynamics, is that the rate of change of heat into the system minus the rate of change of work that is done either by the system, on the system, or out of the system, plus any flow rate, the energy, any accumulation of energy must be equal to what is getting out, and that is expressed in equation 1.5. So for steady flow, dm1 it must be equal to dm2, which is just dm, that is the mass flow rate. It is constant, and hence defining the enthalpy. This is a new terminology, students, take care of this. Enthalpy is designated by H, and H is pressure times volume plus J in the internal energy U. So then we have delta Q dot minus delta W dot plus dm dot into enthalpy 1 plus C1 squared over 2 plus GZ1 should be equal to dm dot in H1, which is the enthalpy plus the kinetic energy state 2 plus potential energy as given in equation 1.6. This is the steady flow energy equation, which may also be conveniently written as Q dot minus W dot is equal to M dot in bracket H2 minus H1 plus a half in bracket C2 squared minus C1 squared plus G in bracket Z2 minus Z1. Take into account that m dot is the mass flow rate and its unit is in kilogram per second, and the unit of the energy component, and H2 is the enthalpy state 2 and H1 is the enthalpy at the entrance, and C2 is the velocity of flow at the outlet, and C1 is the velocity of flow at the inlet. G is the gravitational force, Z2 is the elevation, the height at the exit, and Z1 is the height at the entrance. So in nearly all problems in applied thermodynamics, though changes in height are negligible, thus the potential energy term can be omitted. The kinetic energy term also relatively small in many applications, and the whole equation then normally simplifies. The whole equation simplifies from equation 1.7. we simplify it to 1.8 by neglecting the kinetic energy and the potential energy because they are too small. So don't forget this equation. 1.8 is the most useful equation here. So there are some practice exercise that is meant for you here. So I already attached this with the notes, so I expect you to go through them and find the correct answers. But if you find a trouble understanding either of these questions, then you can ask during our physical classes. So this is a homework for you, and our first assignment, as you've seen there, we have assignment which I expect you to hand over for marking. So next I want us to discuss about the working fluid. The working fluid or substance is the matter contained within the boundaries of a system. When two independent properties of the fluid are known, the thermodynamic state of the fluid is defined. In thermodynamics system, the working fluid can be in liquid, vapor, or gaseous phase. So let's investigate the liquid, vapor, and gas. So consider the pressure volume diagram for any liquid substance. When the liquid is heated at constant pressure, there is a fixed temperature at which vapor bubbles start forming. The liquid starts boiling. The higher the pressure, the higher the boiling temperature. A series of boiling points plotted on a pressure volume diagram appear as a sloping line, as in figure 2.1 here. You can see at pressure P subscript P, it is called P. Pressure P subscript A, it is called Q, and pressure P subscript R, it is called R. So it gives us a slope line that join the points P, Q, and R, which are the boiling points at pressure PP, PQ, and PR respectively. When a liquid at boiling point is heated further at a constant pressure, the additional heat changes the phase of the liquid from liquid to vapor. The pressure and temperature remain constant during the phase change, and the heat supplied is called latent heat of vaporization. The higher the pressure, the smaller is the amount of latent heat required. Dear students, this marks the end of our today's class. Let's meet again in the next lesson.